Imagine something hot. Literal hot, not metaphorical hot. Hot as in temperature. Now, if you're like most people, what you must have pictured would be something like this: a red, hot, glowing piece of metal that is soft enough to be reshaped by a hammer. To strike the iron when it's hot, which means to say to seize the opportunity. But why red and glowing? Most particularly, why do hot things glow? Now, before we talk about that, we must know about the property of light. What is light? Light is a form of energy. Light is an electromagnetic radiation, which is basically a synchronized oscillation of electric and magnetic fields. The electric and magnetic fields are perpendicular to one another and also perpendicular to the direction of its propagation. When people say light, they generally refer to a small portion of what is called the electromagnetic spectrum. The electromagnetic spectrum, or the EM spectrum, has wavelengths ranging from as long as radio waves, which can be up to hundreds of kilometers, to gamma rays, which are wavelengths of less than 10 picometers, which is around a billionth of a millimeter. Now, that's very, very small. The wavelength of visible light, that is the light we can see, ranges between 400 to 800 nanometers. A nanometer is around a millionth of a millimeter. Although light appears to be continuous, but at the elementary level, light is quantized, or we can say not continuous. What this means is that there is a limit to how small a quantity can be. So you can have light in more like discrete packets of energy called photons. Now, you can imagine this as a new brand of chips on your local store, which you want to buy. You can have only one packet, or two packets, or three packets, or none at all. You can't have half a photon, or a quarter of a photon. Light interacts with matter in the form of these packets, but rather than chips, it has energy. The idea of energy quanta was first established by Max Planck in the 1900s. He considered the idea as just a formal assumption, but this idea did, however, solve a problem related to black body radiation, a theory called the Rayleigh-Jeans law, more commonly known as the ultraviolet catastrophe. Yes, a black body is a hypothetical body that absorbs and emits light, but does not reflect light. Learn more about the ultraviolet catastrophe and black bodies in this video by Physics Girl, links in the description. Now, back to the photon. The energy of the photon is given by this equation. Here E is the energy of the photon. The Greek symbol that looks like a V, it's not a V, it's called nu, is the symbol for the frequency of light. And H is the Planck's constant. The Planck's constant has a value of 6.626 into 10 to the power of minus 34 kilogram meter square per second. That is about the number preceded by 33 zeros after the decimal point. Now that's a really, really small number. What this equation tells us that the energy of the photon is directly proportional to the frequency of the wave. Now you can picture this as a man trying to cause a wavy motion on a rope. In order to increase the frequency of his wavy motion, he has to put in more energy into the rope. He has to shake it faster and faster. So the more the frequency of the rope, the more the energy he puts into it. Or that is to say, the energy content of the rope increases. Now, what relation does this have to our initial question? How does this help us know why do hot things glow? It turns out that every object which has a temperature of more than absolute zero emits light, but of course not light we can see. Most of the light emitted by these not so hot objects lie within the infrared region. You, me, your phone, my book, a giraffe, we all emit infrared light. This can, however, be seen by an infrared camera. So technically everything glows. It's just that we can see it. So darkness isn't so dark after all. Now let's talk about heat. What we call heat is simply the average kinetic energy of the atoms. As we start to heat something, like an iron rod, the kinetic energy of the atoms of the rod starts increasing, and hence these atoms start to oscillate faster and faster. They collide with each other. Well, they don't actually collide, but the interaction between the atoms causes it to lose energy in the form of photons. As more and more energy is supplied into the system, the temperature of the body increases and it starts emitting photons of higher and higher energies, that is, higher frequencies. Remember, higher the frequency, higher the energy. Now, as the temperature of the body approaches a temperature of around 798 Kelvin, which is around 525 degrees Celsius or 977 degrees Fahrenheit, which is called the Draper point, the frequency of these photons starts increasing and enters the lower end of our visible band of EM radiation. That is to say, it starts glowing red. Now, it doesn't mean that it is glowing red only, which is not. Most of the radiation it emits is within the infrared region. It only means that now the body is emitting enough radiation within our visible band that its glow is perceivable. As the temperature goes on increasing beyond this point, the body slowly starts to get orangish and then yellowish and then white. If the body can handle temperatures high enough, it may even glow in a slightly blue color. If you like this video, do give it a thumbs up and let us know your thoughts in the comments section below. Thanks for watching.